Unit 16, Acid-Base Equilibria, pages 219 to 222, and this is going to be about Ka and how it relates to Kb. So we're going to focus on the relationship between Ka and Kb for conjugate acid-base pairs, namely focusing on weak acids and bases. So here you have a weak acid, and when it ionizes, you get the hydrogen ion and you get its conjugate base, which is the anion. If you know the Ka, then you actually can find the Kb for the conjugate base. So if this is my acid that ionizes and it has a Ka value, then the conjugate base, you're going to take it, you're going to place it in water, and then it's going to transfer hydrogen over from the water to the anion, and that's going to yield the same acid you had originally, but also hydroxide. And you would want to use a Kb for this equation since it's starting with the conjugate base. Kb for conjugate base. Ka if it starts with the acid. So how can we determine the Kb? Well, you can look at the equilibrium expressions as follows, and you can see that the Ka would equal hydrogen, the anion, over the weak acid. The Kb, if you look at the second equation, would be the weak acid times hydroxide over the base, conjugate base. So if I multiply Ka and Kb, both of these expressions, then everything cancels. The anions cancel, the hydrogen, the acids cancel, and you're left with just the hydrogen times the hydroxide, which is what Kw equals. So essentially, in a nutshell, you could take the Ka and multiply it times the Kb, and you would get the Kw, which you can see stated here, showing you the cancellation and how Ka times Kb equals the Kw. So you really just need to memorize this relationship and make sure you recall that the Kw is 1 times 10 to the negative 14 when we are at 298 Kelvin. We also can have this relationship, the pKa plus the pKb are equal to the pKw, which the pKw is equal to 14. Where the pKa equals the negative log of the Ka, the pKb is the negative log of the Kb, and the pKw is the negative log of 1 times 10 to the negative 14, which again equals 14. So this is a very important example problem we're going to work through that you're going to see over and over and over again, not in this unit, but also in the following consecutive units, or subsequent units. So we want to find the pH of a 0.045 molar cyanide solution given a Ka of 4.9 times 10 to the negative 10 for the acid hydrocyanic acid. So notice we have the Ka for this weak acid. However, we have the concentration of the conjugate base of that acid. So you always want to take, now you may not be given this equation, so you might be expected to write the equation, and you should know that you want to take the conjugate base, you want to put it in water, H2O liquid, yields, realize that the water is going to donate the hydrogen, and you're going to get HCN, which is our original acid, plus, when this gets rid of a hydrogen, we'll end up with hydroxide. Remember that water is not included in our equilibrium. We are going to write, because this is the conjugate base of this acid, we are going to write Kb is equal to hydrocyanic acid times hydroxide over cyanide. And to find the Kb, you're going to take the Kw and divide it by the Ka, and then that would give you the Kb. So the Kw is 1 times 10 to the negative 14 divided by the Ka is 4.9 times 10 to the negative 10 equals, and you get 2.04 times 10 to the negative 5 as your Kb. So now that I know my Kb, and I have my equilibrium expression written here, now I can write my ice table, because the question is going to be find the pH. So we're going to draw our ice table, and initially we have 0.045 of this, 0, 0, minus x plus x plus x, and we're going to end up with 0.045 minus x, x. And what I want you to recognize is that this is what we are most interested in. Finding x, which in this case is equal to how much hydroxide there is. If you take the negative log of x, you're going to get a POH. So make sure you understand that what we're going to get is the POH, but we really want to end up with the pH. So we'll have to do a couple of math steps here. Alright, so now I'm going to plug in and solve for x with my equilibrium expression. So 2.04 times 10 to the negative 5 equals x squared over 0.045 minus x. We're going to consider this an approximation. We're going to get rid of that minus x because this is smaller than times 10 to the 4. So I'll multiply both sides by 0.045 times 0.045, which cancels over here. I'll take the square root of both sides of this equation, and this gives me an x equal to 9.581 times 10 to the negative 4. So recognize that x is equal to our hydroxide concentration. So if I take the negative log of this, because this is my hydroxide ion concentration, I'm going to get a value of 3.02. But remember, that is the POH that we get. When we take the negative log of hydroxide, you get the POH. So we're going to have to take 14 minus 3.02 in order to get 10.98, which is the pH for this conjugate base. We're going to have to verify that this approximation is okay by determining the percent ionization. So we're going to take the value for x, which is 9.581 times 10 to the negative 4. You want to divide it by the original concentration, 0.045, multiply that times 100, and that gives you a value of 2.13%. And remember, it's the 5% rule, so anything less than 5% is acceptable, which means that this is a legitimate approximation and we don't have to go back and use the quadratic formula. Here is our note card for this video. Ka times Kb is equal to the Kw. Remember that Kw is 1 times 10 to the negative 14. So if you have a weak acid, it's going to ionize into hydrogen and a conjugate base. And in this case, when you have the weak acid on the left side, you want to use a Ka value. However, if we have the conjugate base given to us and we want to know the pH based on the conjugate base, you're going to take the conjugate base, you are going to place it in water, and then when the water transfers a hydrogen over, you're going to get the weak acid and hydroxide. And in this case, we have to use the Kb instead. So when the conjugate base is on the left side of the equation, we want to use a Kb, and we can get that by taking the Kw divided by the Ka to get the Kb.